In today's session, let we learn about how many types of hazards are there in your digital circuits. Now, basically, what is meant by a hazard? So thereafter, we will move to your types of hazards and how to avoid that hazards in your digital circuits. So thereafter, we will move to your hazard-free digital circuit implementations. Now, hazard is nothing but unwanted switching transient at your output of your digital circuit. Either it is a combination circuit or it is a sequential circuit. In your combination circuit, it is occurred due to your unequal intervals of your time interval. So, or your uh, applied your inputs. So, based on your applied in your inputs. So, when they are traveled towards to the multi-level inputs, multi-level translation. So then it would take some time delay to reach to that next level. So hence it exhibits that hazards. So where the output will move for a moment, it will move to your actual obtain or your expected output to your unexpected output. So that will be your in your combination circuit. Whereas in sequential circuit, so we have your feedback from your outputs. So due to that feedback, due to that feedback, so it will give you some time delay, and due to that time delay, so your hazards will occur. So this there is a switching transient at your output for a moment of time, so which leads to the unstable states, so or your wrong stable states which are in your asynchronous sequential logical circuit. Now, so let we learn about how many types of hazards are available. So here, so basically there are four types of hazards are available in your digital circuit. So static hazards, so thereafter dynamic hazard and essential hazards. In static hazard, again we have two types: static one hazard and static zero hazard. So four basic types of your hazards are available in your digital circuits. One is static one hazard, second one is static zero hazard, third one is dynamic hazard, and fourth one is your essential hazard. Now static one hazard is nothing but for a moment, so your output will move to your low state. Again it comes back to its logical one state. Static zero hazard is the one, so actual output is zero. For a moment it will move to your logical one state, and again after some time delay it will come back to its stable state, which is zero. So these static hazards and dynamic hazards are occurring here combination circuits, whereas in your sequential circuits, so in your sequential asynchronous sequential circuits, so this is essential hazards are occur. So dynamic hazards are those so where the output will change more than two times. So it is called as your more than two times, means 2 to 3 or 4 times it will change your output. So actual state is one. So now in order to obtain that, so next actual stable state, so first it will move to your zero state and come back to it, go to your one state, again come back to it zero state, and again it will go to your actual stable state, which is logical one. So like this change in your output, if it occurs more than two times or 3 or 4 times, then it comes under your dynamic hazard. So now these occurrence of hazards are detected by using your mapping method. Now let I explain you how you can get that static one hazard. So now here I have transferred inputs x1 equal to 1 and x2 equal to 1. So x3 is equal to 1. So as here I have an OR gate. So where this, because of these three inputs are logical one state. So your outputs of your first AND gate and second AND gate would give you the logical one output. So since here, so x2 is transferred without any logical gate to the first AND gate, but so when it is moving towards, so we can obtain your input of your third AND gate. One input comes from your first AND gate, the other input comes from your second AND gate. So now when x2 is traveled through your AND gate, it has to pass only one level. So only in one level you have a one AND gate. Whereas in your the second AND gate, so the second input of your OR gate will travel from your x2 through your 2 level. So since it has to reach first NOT gate and then it has to move to your as your output of NOT gate output as an input to the AND gate, and the output of your AND gate is connected to the 2. So 2 level, so your x2 has to travel through your 2 level, where x2 on your first AND gate travels your only 1 level. So since that, so here, so actual input is 1. So now 1 is transferred. So for a moment it will transfer to your 0 due to your delay. So now that delay causes here. So now it is moving towards to the 0. So when it is 0, so when I change your x2 input with a 0, so now, so it has to move that output to logical 1 state. So since that, so this AND gate will give you the logical 1. So logical 1 output. So initially we got a output which is 1. So now it is at 1 state. Now upon changing your x2 for a moment it is 0. Due to this NOT gate, it will move to your logical 1 state. So second output, instead of it has to move to your 0, it will move to your logical 1. So since of this 0 input, so here the first AND gate has to give this 0 output. So now, hence here, so here output of your, so because of this time delay, so now this, instead of altering this input to logical 1, so this output would give you the 0 output. So NOT gate output will give you only the 0. So since of that, so here we could have your output which is equal to 0 output, and here we got your output of your first AND gate is 0. Now, so due to this is total 0 0 as your two inputs of your third AND gate, for a moment, so your output of your this circuit will move to your logical 0. So after some time delay, so here now the NOT gate will invert your input, so which is connected to 0 input is now it is connected to logical 1. So since of these three inputs are 1, now it changes to logical 1. So hence, so here you obtain your the actual state which is comes from your 0 to logic 1. So like this, so for a moment it will move to your 0 state, and after that, so it will again come back to it logical 1 due to this time delay element which is a NOT gate. So this type of hazard, so that moment of change, a small moment of change in your output which is moving from 1 to 0, it is called as static 1 hazard. So in order to avoid this static 1 hazard, we are going to follow your reverse mapping. So now here in reverse mapping, by using your redundant term, you can avoid that. So now, so here my expression for this circuit is equal to, so here we have the first AND gate will give you the product term of x1 x2, and second AND gate will give you the product term of your x2 bar into x3. So now your R output is equal to summation of your x1 x2, the product terms of x1 x2, x2 bar into x3. Now, so using a reverse mapping, so let me pair your find out your minterm. So since it is belongs to x1 x2, the common variables are x1 x2 both are ones. So hence it belongs to the, so where it is not having your x3 value. So x3 is not common for both these minterms. So 1 1. So 1 1 we have it on your x1 x1 x2. So here x1 x2 are, so 1 1. So x1 is the most significant and x2, x3 are your least significant variables. So the possibility is x1 is 1. So x1 belongs to this 4 squares, where above 1 is 4 squares is 0. So hence, so the minterm belongs to that 4, the below row which is logical 1 on your x1. And x2 is 1 in the column of your third column as well as your fourth column. Hence minterms are placed on these two cells, so where those are coincident. So next we need to find your x2 bar and x3. So since x1 is not there here, so x2 is 0 and x3 is 1. So hence the minterms are in your first cell as well as in the fifth cell. So now, so this is your actual reverse mapping we have done using your product. We found your minterms, and then we found that, so they are adjacent using your 2 square adjacency. So hence we have your 2 pairs. Now, so in your K-map minimization simplification, we are not doing the mapping of your fifth minterm with the seventh minterm. So, but those are called as redundant term. Once it is covered, so we will ignore those terms. But in order to avoid this hazards, so let me introduce that redundant term in this product term or SOP, or you can also convert this into standard SOP. So then we can have your introduction of your one more term, which is called as your which is the which is here the min term which is added with along with your x1 x2 x2 bar x3 x1 x2 plus x2 bar into x3. So we could also have one more redundant term which is x1 into of x3 x1 into x3. Now let I connect x1 x3. So this product term of redundant so will not move your output goes to your logical zero state since over a moment of time. So if it is changing 1 to 0, so x2 is changing 1 to 0, so not it would take your time to hence it is giving you zero output. So both will give you zero outputs as your inputs to the OR gate, hence y output become 0. So but here now x1 is equal to 1, x3 is 1, so which are connected with the 1 level only. So hence these two ones are 1. So output of this third AND gate will give you logical 1 output. As you introduce your third product term x1 x3. So if these two are zeros, so if and x1 x the redundant term is giving 1, so output may not go to your zero state. So it will be for a duration of time interval on your output, so it will move to your 0 earlier, but now so due to this so it will be at logical 1 state, so it may not go to your logical 0 because of this introduction of your redundant product so like this, so we can avoid your hazards static 0 or your static 1 hazard in your combinational circuit, whereas in sequential circuit it may not be possible to remove your hazards by just adding your redundant terms. So that will be your an essential hazard. These essential hazards are caused due to your unequal delays at your along with your two or more paths that are originated from your same source. So hence in order to correct that, so we should not add your redundant gates. So hence we have to follow your adjusting your delay in your affected paths. So each feedback path should be examined carefully to avoid your hazards in your asynchronous sequential circuits.